Okay, so this video is a sort of addendum to the previous one about linear drag, mainly aimed at addressing some misconceptions that are published in some books that we will not name. So last time we tackled the case of linear drag, where the magnitude of the resistance is proportional to the speed of the ball, which is the magnitude of the velocity vector. We'll put some numbers onto our velocity vector to start with here, the good old 3, 4, 5 triangle. So the horizontal velocity is 4, the vertical is 3, giving a total speed of 5. We'll put k at 0.5, meaning that the drag vector is half the length of the velocity vector, only it points the opposite direction. So its length must be half of 5, which is 2.5. And what we did last time was we used similar triangles. We saw that they would force the horizontal component of the drag to be half of 4 as well, which is 2. And the vertical component to be half of 3, which is 1.5, so that k factor applies to the components separately. So the whole purple triangle was just then the green triangle scaled by k with all its directions flipped, which we can write like this. The velocity vector, x dot y dot, scaled throughout by negative k, which in this case again was negative 2, negative 1.5. Now, quadratic drag is almost the same, starting point at least. It's just the magnitude of the drag is proportional to the square of the speed, not just the speed itself. And the really tempting thing to do, which some people have done, but a really wrong thing to do, is to try and copy the pattern from linear drag, and simply use negative kx dot square and negative ky dot square as the components of the acceleration vector. So in this case, 4 square is 16, half of that is 8, 3 square is 9, half of that is 4.5, and we'd get this vector here. Now let's quickly draw that so we can see clearly why it is so wrong. There's our 8 going in the negative direction, there's our 4.5 going in the negative direction, giving this as the proposed resistance vector. But we know that resistance direction is always opposed to the velocity, right? And this one just straight up isn't, it's pointing the wrong way. Okay, also its magnitude is supposed to be k times the square of the speed. Okay, which in our case, it's meant to be half of 5 square, which is 25, and that's meant to be 12.5. But if you apply Pythagoras to this red triangle, you get like 9.2 or something. Okay, so this red vector fails miserably to describe the situation in both its length and its direction. Okay, it's sort of like pretending that squaring the length of a shape somehow keep it in proportion. It doesn't. Okay, so that's why this all fails. Okay, so what's meant to actually happen? Well, the key is to keep the direction perfectly opposed to the green velocity vector. We know the length we're aiming for is 12.5, half of 5 square, so we're meant to simply scale the purple vector until it reaches that desired length. We could then use similar triangles to work out what the horizontal and vertical components are meant to be, which you could pause and do if you wanted to, but we won't do that. We'll move to a general case now. Okay, so we'll change the labels on our velocity vector to the standard x dot y dot, and then the vector v, where after this purple vector whose length is k times the length of v squared. Okay, so that quantity there is just a length, it is not yet a vector. How would we get the vector? Well, the length must be this k times length of v square, that guy here. Then to make it point opposite to v's direction, we need to multiply it by the negative of v's unit vector. Okay, so the negative ensures it's pointing against v, and then multiplying it by v means that it's pointing the right way. Scaling by the reciprocal of v's length ensures we haven't messed with the length that we so carefully established. So now the algebra of this, the length of v downstairs cancels one copy of the length of v outside. They're both just scalars because they're lengths. And that leaves us with the velocity vector v scaled by negative k times the length of v. That's our scalar. Okay. If we want to be a bit more explicit with the vector v, we could rewrite it as x dot y dot, with the outside stuff, again, all being scalars. They are all just numbers there, the k and the length of v. So that gives our horizontal and vertical components. The horizontal would be negative k times the length of v times the horizontal speed, x dot. And the vertical is just negative k times the length of v times the vertical speed, y dot. Okay, and that gives the final acceleration vector, which is really just the original velocity vector v, but scaled by negative k, and scaled by the length of v itself. In general, this acceleration vector leads to some differential equations that are very difficult to solve, and I can't imagine you'd be asked to. Okay, so maybe there could be some numerical questions about the acceleration or the resistance force when you're given already the horizontal and vertical speeds at a particular point or something like that. Okay, but that's how we're meant to properly set up the situation of quadratic drag. So that's all. See you around.